So, good morning to one and all. Dear friends, today we have discussed the theory of long column by Euler's theory, and second is the using the rankings theory or ranking method. So, as we know that generally column, when we consider the column, it is a vertical element, but when we consider the strut, it may be inclined or it may be horizontal. Of course, it is a compression member. So, the column may be short or column may be long depending on the aspect ratio, or we can say that the slenderness ratio. So Euler's theory is applicable to only long column, while the ranking theory is applicable to both long column as well as short column. So long column may fail due to the buckling or bending effect, or we can say that the even though the load is there, but the length of the column is so large or so long because of the length, or we can say that the slenderness ratio, column may buckle or bend, while short column may fail due to the crushing. So the Euler's column theory, there are certain assumptions when we analyze the column, long column. The column is perfectly straight and having uniform cross section throughout. The column is subjected to purely axial load only. That means the bending is not allowed. Perfectly straight and having the uniform cross section throughout. Column material is homogeneous, isotropic, and elastic. That means it obeys the Hooke's law. The length of the column, of course, when we consider the long column, is very large. Stress due to the direct load is very small and neglected. Failure of the column occur only due to the buckling. These are the few assumptions which are used in the analysis of the column or column subjected to the purely axial load, but for the long column. There are definitely four conditions for the when we consider the column. Both ends are hinge, both ends are fixed. One end fixed, other is hinge, and last is the other one end is fixed and other is free. Generally, when we consider the building, if there is a intermediate story, that means the column with the bottom beam is there, top beam is there, then it is treated as a fixed one. Sometimes we know that for electric pole, or we can say that the foundation without the beam, and it is uh, there are a column at the ground level or plinth level. In that case, we can see that it acts as a that is the fourth condition. One end is fixed while other is we can say that the with other is free, not hinge. uh, Generally in mm, many apartments, what happens, there is no walls at the ground floor. Generally we have given provision for the parking. In that case, we can say that the both ends are hinge. So these are few examples, but definitely this is the bending effect. When we consider the both ends are hinge, in that case, total height, that is the length of the column, is equal to effective length of the column. LE is equal to L. This is the first condition. Second one, due to the column is fixed at both ends, and that's why we know that the deflection is not allowed at the support A and at the support B, that is the fixed end. Therefore the deflection is less, and in that case the effective length is equal to L by 2. Third condition, one end is fixed and other is free. In that case, of course, one end is fixed and other is free. In that case, it is L divided by under root of 2. And third condition, last condition, one end is fixed and other is free. That is the just like a cantilever. In that case, LE is equal to twice the length. That is the twice the height of the column. These are the four conditions. So let us have the first condition. In the first condition, of course, we have find out the crippling load or critical load, or in that case, we can say that the load which try to bend the column. So here P, we have considered the critical load on the column. Y is the deflection, that is the bending at a distance of x meter from the bottom end A. Both ends are hinge. So moment due to the critical load is equal to, of course, we can say that the this load multiplied by perpendicular distance y. So P multiplied by y in the anti-clockwise direction. So it is minus P into y. That is the moment. And again we know that as per the moment equation, ei into d2y by dx square is equal to moment, that is minus p into y. So we have refine this, change this, uh, we can say that the term, and we get the ei into d2y by dx square plus p multiplied by y is equal to 0. And this equation, so ei will be divided by ei, so we get the d2y by dx square plus p by ei into y is equal to 0. And for this, the general solution of this differential equation is y is equal to a cos x under root of p by ei plus b sin x under root of p by ei, where a and b are the constant of the integration. So when we consider the at x is equal to 0, that means we can reach at the point a here, and therefore at x is equal to 0, y is also equal to 0. And when we put these two values, we get a is equal to 0 in this equation. Okay. Uh, we have, we are getting the equation y is equal to as a 0. That's why this term is 0. So we get the b sin x under root of p by ei. Now we have applied the second equation, second condition. When I have considered here x is equal to L, that means we can reach at point B. What about the y? Y is again 0. X is equal to L, y is equal to 0. And in that case, um, 0 is equal to b sin L multiplied by under root of p by ei, as x is equal to L. Therefore, can we say b, either b is equal to 0 or sin L under root of p by ei is equal to 0. But when we consider b is equal to 0, what happens? A is 0, already a is 0, b is 0, then y is equal to 0. That's mean we can say that the column never buckle. But here it is observed that the column buckle because of the slenderness, and therefore we have taken the second option, that is the sin L under root of p by ei is equal to 0. And we know that sin 0 is equal to 0, sin 180, that is pi, is equal to 0, sin 2 pi is equal to 0, sin 3 pi is equal to 0. But in this case, when we consider is equal to 0, we get the no answer. But we have considered the practical value, that is the first practical value is pi. And therefore, we have considered L into under root of P by EI is equal to pi. So we get the P is equal to, that is the crippling load or critical load or maximum load where the column start buckling is equal to pi square EI divided by L square. Now this is the critical load if the both ends are hinged. So for both the ends are hinged, we can say that L is equal to L, and therefore the general formula which is applicable to all the four cases, both ends are hinged, both ends are fixed, one end fixed, other is hinged, and last is the one end fixed, other is free, is P is equal to pi square EI divided by L square. We have considered this equation. Okay, and that's why once we have put this value in this formula, L is equal to L, L is equal to L by 2 for the both ends are fixed, L is equal to L by root 2 for the one end fixed, other is hinge, and last L is equal to 2L when we have considered one end fixed and other is free, and we get the crippling load for all these four cases. Okay. Now similarly, we have find out the crippling stress. So for the crippling stress, we know that the crippling load is equal to pi square EI divided by L square. We have already find out. So pi square E into I. I means the it is the moment of inertia, that is also equal to area A into K square. K is the radius of gyration. Okay, and therefore I is equal to, we can say that the second area of the second moment of area. So I is equal to AK square. So eliminate this I by AK square divided by L square. So again we know that K square we have taken in the numerator. So L square divided by K square, and again um, pi square E into A, then LE by K whole square, because this is LE square divided by K square. So LE by K, what is LE by K? LE by K is the slenderness ratio. So, and the stress corresponding to the crippling load is given by stress is equal to load divided by area. Of course, compressive load divided by area. And this is the P, that is the pi square EA divided by LE by K whole square. So, P by A will be vanished, and we get the crippling stress, that is the maximum stress, is equal to pi square E divided by LE by K whole square. Okay, this is the crippling stress. Now, what is slenderness ratio? Slenderness ratio is the ratio of the actual length of the column to the radius of the gyration of the column. It is called as the slenderness ratio. So, what are the limitations for the Euler's formula? Why we have considered Euler's formula is applicable only for the long column? Because when we have considered the crippling stress, that is equal to pi square E divided by LE by K whole square. In that case, L by K is the slenderness ratio. Okay, but we know that for the mild steel, for example, when we consider the mild steel, the critical stress or maximum stress is 330 Newton per mm square, or in MPa, modulus of velocity is equal to 2.1 into 10 to the power 5. So we can put here in this equation, that is the crippling stress is equal to pi square E divided by LE by K whole square. In that case, we have considered the both ends are hinged, and that's why LE is eliminated by L. So L by K whole square. In that case, it is observed that by putting the value of E, the value of trace, that is the crippling trace, maximum trace. Crippling trace is equal to the compressive trace or maximum trace, which is 330. So we get the answer L by K is equal to 79.27, which is closer to 80. Hence, if the slenderness ratio is less than 80, specifically for the mild steel column, both ends are hinged, then the Euler's formula is not valid. And therefore, this is the limitations of the, we can say that the Euler's formula. So remember this. This question is generally asked in also MPSC. Write down the or prove the when the LE by K less than 80, Euler's formula is not applicable. This is the proof. So here, as we have already discussed, this four cases, both ends are hinged. One end fixed, other is free, both ends are fixed, one end fixed and other is hinged. These are the formulae. We have just put the value of LE by L for the both ends hinged. For one end fixed, other is free, 2 times of L, and for both ends fixed, it is L by 2, and one end fixed, other is hinged, it is L by under root of 2. And we get the one more important thing is that when we analyze this using the Euler's theory or ranking theory, the value of I should be least, because if the value of I is least, then there is a chances of the buckling in that direction. Therefore, we can find out the Ixx and Iyy, and we have taken the least value for the calculation of the crippling load. So here there is one, we can say that the problem, determine the Euler's crippling load for the I section. I section joist, it is a steel section, 400 mm by 200 mm by 10 mm and 5 meter long, which is used as a strut with both ends are fixed, and the modulus of velocity is 200 GPa. The figure shows the cross section of the joint. This is the cross section. So first of all, we can find out the Y. But here we know that this section is symmetrical about the x-axis and y-axis, and that's why the CG of the section along x-axis, it is 400 divided by 2, and for y-axis it is 100, because this is 200. So no need to find out separately. A1 separate this, we have considered the rectangle one, then another rectangle and another rectangle, and find out the Ixx, Iyy. So for Ixx, we have considered the 3 section, or we have considered the total rectangle. Generally, for the unsymmetrical section, we have considered the 3 rectangle, 1, 2 and 3, and find out the Ixx, that is equal to BD cube by 12 plus a H square. H is the CG of the individual section and CG of the we can say that whole section, and square of that. So in this way, we have find out the Ixx, which is 1.97 into 10 raised to the power 8 to the power 4, and Iyy. These two sections are same. That's why 2 times of BD cube by 12 plus 200 into this one. Again, the value of H is 0, and that's why we have get BD cube by 12 plus BD cube by 12. So the Iyy is 1.3365 10 raised to the power 7. So it is observed that as compared to Ixx, the lowest value is Iyy. Therefore, we have considered the I is equal to Iyy. So here both ends are fixed. That's why L is equal to L by 2, and so 5 meter length is there, so 5 meter divided by 2, it is 2.5 meter, and the crippling load is equal to pi square ei divided by L square. L is equal to 2.5 meter, convert it into pi square into E is equal to already given 2.1 into 10 raised to the power 5, and I is equal to Iyy. So we get the value of P, that is the maximum load, crippling load, that is the 4432.08 kilonewton. This is the problem. So thank you very much. Have a nice day.